Welcome back to JCB EduBuild Solutions. Today, we tackle sanitation, plumbing design, and installation, Part 2. To understand a building's plumbing, we have to track the water through its entire life cycle. We are going to trace that path chronologically across 4 interconnected systems: water supply, drainage, venting, and private sewage. We start with the water supply system. While wastewater relies on the natural pull of gravity, delivering clean water throughout a structure requires a continuous pressurized distribution network to push water upward against gravity and out of the fixtures. This page highlights where pressure fails. Inadequate pressure, under 103 kilopascals, causes friction loss. Excessive pressure is over 551 kilopascals. Fixing extremes requires mechanical intervention. Below 103 kilopascals, install an elevated tank with a booster pump. Above 551 kilopascals, an approved pressure regulator is required. This diagram illustrates the safeguard if pressure drops. A sudden loss creates a vacuum, pulling wastewater into the clean supply, a hazard called backsiphonage. The primary defense is the air gap, an unobstructed vertical distance between the pipe's lowest opening and the fixture's flood level rim. Proper water supply design is a strict balancing act. You must maintain sufficient delivery force while engineering physical gaps to protect the potable water from fixture contamination. Once the water is used, we shift from the push of supply to the pull of drainage. The core objective here is self-scouring, designing pipes that flush out solid wastes along with the wastewater, essentially cleaning themselves. This table breaks down the exact horizontal slope required to achieve that self-scouring effect, based on pipe diameter. Pipes smaller than 102 millimeters require a 2% slope. Pipes equal to or greater than 102 millimeters require a 1% slope. And massive pipes 204 millimeters and above require only a 0.5% slope. Notice the inverse relationship here. The larger the diameter of the pipe, the flatter the allowable slope. This diagram shows the transition out of the building. The house drain collects the interior waste, but once it extends beyond the outer wall, it becomes the house sewer. The code is explicit here. The building sewer must be laid at least 0.6 meters below the finished surface of the ground, and it cannot be smaller than 150 millimeters in diameter. If these slopes are miscalculated, the entire drainage balance fails. If the pipe is too flat, the water pools and causes clogging. If the slope is too steep, the water rushes past, leaving the solid waste behind. But drainage pipes cannot function smoothly without air. As wastewater rushes down a pipe, it creates a vacuum behind it. Without a venting system to supply air, that vacuum will pull the water out of your P-traps, destroying the trap seal and allowing foul sewer gases into the building. This reference diagram clarifies 2 easily confused components. The vent stack is the dedicated vertical pipe installed primarily to provide air circulation to the drainage system. The stack vent, however, is simply the extension of a soil or waste stack above the highest horizontal drain connected to it. For tall buildings, we have to manage intense pressure changes within these vertical drops. This requires a yoke vent, a pipe connecting upward from a soil or waste stack into an adjacent vent stack. The code requires this specific connection in every 5th floor. Let's test this. If you are designing the plumbing for a 15-story building, which floors require a yoke vent? You will need to place them on floors 5, 10, and 15. Venting functions as a continuous pressure equalization mechanism, protecting the physical water seals across every fixture in the structure from siphonage and trap seal loss. Finally, if the public sewer is not available, the waste reaches its final destination, the private sewage disposal system, commonly the septic tank. This section details how to size that tank. The liquid capacity is calculated based on 3 distinct criteria: the number of bedrooms or apartment units, the estimated design flow rate, or the total number of plumbing fixture units. The core code constraint here is absolute. You evaluate all 3 criteria, but your final capacity must always be based on the parameter that yields the largest volume, whichever is greater. If you underestimate this capacity, the system cannot hold the effluent long enough for solid separation to occur. This results in untreated waste overwhelming the leaching field, leading to severe system backflow and toxic soil contamination. Final sewage capacity cannot rely on averages. It must be engineered to handle the absolute maximum potential load of human occupancy in that building. Let's lock in the numbers. Supply pressure is strictly bounded by 103 and 551 kilopascals. Drainage slopes step down from 2% to 1% to 0.5% as pipes get larger. Yoke fence tie in every fifth floor, and septic capacity always defers to the greatest variable. Kung may lalabas sa exam, dito umiiko tung system. If you want to dive into the detailed design computations and practice with actual board exam problems, send us a message. Thank you, JCB viewers. Make sure to follow our page for more step-by-step content and access to our free reviewers. Memorizing these precise operational thresholds is the exact bridge between theoretical plumbing knowledge and passing your Master Plumber Licensure examination. Keep practicing, and we'll see you in the next lesson.